All right, hopefully those equilibrium laws felt pretty good once you put them into practice. Now let's consider putting in numerical values for the concentrations or for the equilibrium constant itself in order to algebraically solve for unknown values. Now, ultimately, when you're calculating equilibrium constants, you are substituting in a number of different things that you know. For example, you're substituting in correct. Now, notice this is underlined. I'm going to even make a big red square around it. The correct equilibrium molar concentrations. Guys, if you start plugging in the initial equilibrium concentrations or how it changes, all your numbers are going to end up wrong. This is an equilibrium constant. So if you're using any concentrations that exist at a time that is not equilibrium, it's not going to work. So really focus in on that. Anyway, we're going to substitute in correct equilibrium molar concentrations and potentially, depending on what you're looking for, even substitute in the actual equilibrium constant itself to help us figure out the concentrations of the unknowns, right? Okay. So, for example, what if we go back to the world of an ice table again, and we are dealing with nitrogen monoxide gas and oxygen gas again, forming nitrogen dioxide gas. At this point, we have the initial concentrations of all of them. That's not good enough. We need the equilibrium concentrations of each different reactant and product. At this point, I've only got one of them, so I need the other two. But I do have the hint of how they are changing. If I look at this, I can see that the O2 gas is going to go, now look at the numbers, 0.066 to 0.017. That's a decrease. So that means it went down by a factor of 1x. Why 1? Because the coefficient in front of that oxygen is 1. Okay, so calculation-wise, I can take that and I can logically look at it and be like, all right, that means for the O2 gas, we're going from 0.066 moles per liter, molarity, minus an X to equal 0.017 moles per liter. Algebra, figure it out, X is equal to 0.049 moles per liter. Store it in as X if you want in your calculators. Have a look. If oxygen is a reactant and it's going down in concentration, then the other reactant, nitrogen monoxide gas, is also going to go down. However, it's going to go down by a factor of 2 because of the coefficient. All right, so we'll take that, go minus 2x, knowing that x is equal to 0.049 moles per liter. Work it out, calculate it, we get 0.045 moles per liter. Oh, we're getting somewhere. Now we know 2 of the equilibrium concentrations. We still need, however, the product's concentration at equilibrium. So once again, look at that coefficient, 2 nitrogen dioxide gas. So that means it is not going down by that, it's the product. If the reactants go down in concentration, the product has to go up by 2x, 2 because of that coefficient, just like what happened on the other side. Okay, number crunch it in, 0.068 moles per liter plus 2 times 0.049 moles per liter. We're going to get a total of 0.166 moles per liter. Again, feel free to use that capital M for molarity representing molar concentration. Okay, so highlighted in yellow is the molar concentration at equilibrium. Next step here then is before you can do the calculation for Kc, you must show the equilibrium law. Guys, I will look for this every time. I will give you a mark for the equilibrium law. Take the time to do it properly. So I want to see, no numbers in yet, but the actual law. NO2 gas, the coefficient is 2, so it needs to be squared, divided by the concentration of nitrogen monoxide gas. Again, we've got a what am my marker doing here? We've got a coefficient of 2, so it needs to be squared, times the concentration of the O2 gas. Now we can start to plug in. Equals, use what I highlighted in yellow. Those are your equilibrium concentrations. 0.166 moles per liter squared, divided by 0.045 moles per liter, also squared, right, because of that coefficient, times the concentration equilibrium of oxygen, 0.017 moles per liter. Don't forget, the whole top is divided by the entire bottom. Be careful that you don't mess that up, please. Our answer is going to have to be to how many sig digs? Well, guys, if you look back and consider what we have, it needs to be to 2 sig digs because that's what we had here. Okay, so number-wise, we've got our 2 sig digs that are going in. Kc is going to be equal to 800.46. It keeps on going. In other words, equal to 8.0 times 10 to the 2. And that is our official equilibrium constant. Now, this is key, guys. Equilibrium constants have no units, all right? So whenever you calculate the equilibrium constant, you do not include units. The reasoning for that is, again, that technically each of these concentrations is actually done by a ratio over its activity, so the units do end up completely canceling out. We just don't show that process, that step in Chemistry 30. It's a complication that it doesn't help with your understanding, all right? But ultimately, what you need to recognize, again, equilibrium constants always are unitless, do not have units. And here is our end answer. Okay, let's try another one. What if we do a little bit of a spin on it? What if I give you the equilibrium constant right at the beginning, and then I tell you, hey, at equilibrium, that's why there's only an E there. I don't have the I or the C, the initial or the change in concentrations. At equilibrium, I'm giving you the concentration of the products. And the whole point of the question is, hey, what is the concentration of the dinitrogen tetraoxide? Ultimately, there's still one unknown. So this is doable from an algebraic perspective. How do we do it? Well, step one is we need an equilibrium law. And the equilibrium law states that Kc is equal to the concentration of the nitrogen dioxide gas to the exponent of its coefficient squared, divided by the concentration of the dinitrogen tetraoxide gas. All right, there's our equilibrium law. Now what? Well, now we need to get this concentration by itself because that's what we're solving for. Fairly simple algebra, guys. We're going to multiply by that on both sides. All right, I'll show the process for this. I think a lot of you can do algebra like this on your heads. All right, okay, times by that. What you do to one side, you do to the other. If my pen will let me write it in, N2O4 gas, these ones cancel out. Then we need to, of course, divide out by the Kc so that we can get the N2O4 by itself. Equilibrium constant cancels out. End result, we have concentration of N2O4 gas is equal to the concentration of nitrogen dioxide gas squared divided by the equilibrium constant. There it is. A rearranged equilibrium law that we can now calculate with. So at this point, of course, you just plug in what you know. It's going to be equal to the concentration of the nitrogen dioxide, so 0.934 moles per liter, or capital M if you want, squared, divided by the equilibrium constant, which is 375. Sig dig wise, both of those have 3, so our answer is going to have 3 significant digits. N2O4 gas is therefore equal to, concentration wise, 2.33 times 10 to the negative 3 moles per liter. And there you have it. So a super useful tool, being able to have that equilibrium law and the equilibrium constant to figure out concentrations of different entities within the context of a balanced chemical reaction. All right, let's do one more that has a bit of a difference in the manipulation. What about this one? Once again, we have a scenario where I give you the equilibrium constant. And in this case, I'm going to give you the concentration of the dinitrogen tetraoxide instead and say, hey, can you figure out what the concentration of the nitrogen dioxide is? So it's a little bit of a flip on ideas, right? So ultimately, the equilibrium law ends up being the exact same. NO2 gas squared, it's a square bracket 2, divided by N2O4 gas concentration, okay? Now in this case though, we are trying to get the NO2 gas concentration by itself, not squared, right? We need to get rid of that. How are we going to do that? Just again, simple algebra, right guys? So we're going to multiply by the N2O4 gas concentration on both sides. And now once we've multiplied by that, how do you get rid of a squaring? Well, by taking the square root. That's what's going to cancel it out, right? Okay, let's clean this up a little bit. End result, we will have the concentration of NO2 gas is equal to the equilibrium constant Kc times the concentration of the N2O4 gas, all square root. And the square root has to go over the entire entity. Otherwise, you're going to get a wrong answer. Okay, plug in what you know. We have all under the square root, my equilibrium constant, 0.035, no units, times the concentration of the N2O4, which is 0.214 moles per liter, is given to you in the questions. Number crunch away, you get 0.086544, keeps on going, moles per liter. Look back, we need 2 sig digs because of that equilibrium constant. So our end answer, the concentration of NO2 gas is going to be 8.7 times 10 to the negative 2 moles per liter. Done and done. In the scheme of things, guys, this is totally doable. It is honestly fairly simple algebra. It's just a matter of correctly creating those equilibrium laws. Done and done. Practice for this one that I'd like you to do, please, is essentially the rest of the assignment. We've got 1B, 2D, and number 4. Now, there's a couple other questions we haven't covered yet. We'll talk about those after the next podcast, but make sure you try these first and are able to utilize those equilibrium laws in a calculation type format. For every question related to this, always write the equilibrium law first before you start substituting in any values. Good luck.